Welcome to this explainer. Today, we are diving deep into Cambridge IGCSE computer science exam strategies. And honestly, we're going to treat this like a high-tech mission briefing. We aren't just doing a boring review of concepts here. No, we are uncovering exactly what examiners are secretly demanding from your answers and how you can literally hack the mark scheme to get full credit. If you have ever walked out of an exam feeling like you knew the material but somehow still dropped points, yeah, you are in the exact right place. It turns out the mark scheme is actually looking for something incredibly specific, and once you discover what that is, it changes absolutely everything. So let's jump right into it. Okay, so it is absolutely wild, but 9 out of 10 students get standard hardware and data transfer questions wrong in the exact same way, and it quietly costs them the grade. I want you to picture this catastrophic, but honestly, incredibly common exam scenario. A student sits down, they read a question about data buses, and they write this seemingly correct, logical answer. But they completely fail the examiner's reality check. They walk out thinking they totally nailed it, only to see a massive red cross on their paper weeks later. So let's look at this trap on the big screen before we fall into it ourselves. All right, here is the classic red pen error in action. You can see a vague student answer on the left. It makes the data go faster. I mean, that sounds okay in casual conversation, right? But relying on vague, generic labels like that completely destroys your chance at full marks. Now, compare that to the examiner's actual demand on the right. Transmits data between internal hardware components using a bidirectional data bus. It is night and day. The examiner isn't looking for a casual summary. They are testing your ability to explain the exact step-by-step movement of data using syllabus-safe vocabulary. So how do we actually bridge that gap? Well, we do it by adopting this 3-layered learning model. Instead of jumping straight into memorizing complex terms, which, let's be real, is super overwhelming anyway, Layer 1 starts with everyday language. You just ask, what practical problem does this actually solve? Then, in Layer 2, we upgrade to the technical vocabulary, locking in those precise definitions like bit depth or sample rate for image resolution and sound. And finally, Layer 3. This is where we shape all of that into a high-scoring, context-specific exam response. We are moving from simply knowing what a thing is to explaining how it works and why it matters when you're under pressure. Now, a massive part of building that Layer 3 exam response is translating examiner jargon. Command words are literally everything. If a question says state, or actually scratch that, even if it says define, sure, you can be concise. But if the command word is explain, a simple description just is not going to cut it. Explain means you must actively provide the step-by-step mechanism of how it works and justify why it matters in the specific context they gave you. You're explaining the logic and the flow. If you just describe basic characteristics when they ask you to explain a process, you are leaving guaranteed marks sitting on the table. Let's look at a full-screen example of this framework applied to CPU core functions. It really changes everything. Instead of blindly memorizing the fetch, decode, execute cycle, we use a simple, student-friendly 4-step exam method. First, identify and classify the exact concept. Second, sequence the technical explanation logically, step by step, so you don't miss marks on the process. Third, and this is huge, root it deeply in the provided scenario. Like, is this CPU running a school database, or is it running a factory robot? And fourth, explain the how and why. Every single step must logically lead to the next. What's super fascinating is how universal this method is. Take checksums and check digits, for example. It is so easy to fall into the trap of shallow memorization here. But by layering your knowledge, you upgrade a basic verification label into a full marks breakdown. You start by explaining the practical problem, making sure a barcode scans correctly at a grocery checkout. Then you step up to the technical mechanism, explaining the chronological data process and the calculation. You aren't just saying it checks for errors, you are detailing the algorithm that proves the data's integrity. All right, let's do a rapid-fire mistake clinic, because a crucial part of this is knowing what not to do. These are the primary culprits for hemorrhaging points on exam day. First up, naming a component, like just saying keyboard, without explaining its actual function in the scenario. Second, the classic trap of confusing memory, which is fast and temporary, with storage, which is slow and permanent. Don't mix those up. Third, confusing data validation with data verification. They are completely different things. Fourth, using generic wording like it works or makes it faster. No way, the examiner hates that. And finally, ignoring the specific exam scenario. A robotic arm in a car factory has entirely different constraints than your local school network. So to resolve these pitfalls, we use a structured correction strategy for topics like buses and data transfer. Think of it as a triple pass revision cycle.
You secure the definitions, you rehearse the worked diagrams, and then you adapt your answer to whatever changing exam scenario they throw at you. By doing this step by step, we explicitly ensure we never confuse logic with arithmetic processing, or, mix up address buses with data buses. And most importantly, we never fail to anchor our definitions to the context. High marks require moving past those short, vague labels and providing real, robust process explanations.
And this transitions us perfectly into input, output, and storage. Following a structured solution path means you consistently contrast nearby concepts. To prove to the examiner you aren't just guessing terminology, you have to explicitly distinguish between similar terms. When you contrast memory against storage, you show the examiner you truly understand volatility and access speeds. When you explain an input device, you need to pinpoint the exact task requirement, like capturing a physical key press and translating it into a digital signal, rather than just writing down some generic, vague label. Okay, before you write down any final technical response, I want you to run it through this 4-question self-check. Number 1, what exactly is it? Give a clear identification and definition. Number 2, how does it physically work? Detail the chronological process and mechanism. Number 3, where is it used? Apply it strictly to the contextual scenario given in the prompt. And number 4, why is it better or worse? Provide a solid justification against the alternatives. I promise you, if your answer hits all 4 of these steps, you are securing every possible mark. Applying this 4-step check to online communication is a real game changer because it ensures that tricky boundaries are definitively separated. For example, separating a protocol from a service is absolutely vital. A protocol is the set of rules, whereas the service is the practical application. By formatting your knowledge into concise responses that separate the description from the explanation, your answer is going to align perfectly with what the mark scheme expects under pressure. As we reach the ultimate examiner's playbook here, the concept of a 2-student duel perfectly illustrates the stakes. Picture 2 students taking the exact same test. The student with the safe but shallow description, they get the red pen, but the student with the technical, reasoned explanation, they get the green check. It turns out that context is king. The difference between passing and perfection is often just anchoring your scientific reasoning to the retail store, or the hospital, or the embedded system mentioned in the text. Don't fixate on a familiar device name. Focus on the core mechanism and the sequence. Whether you're dealing with embedded systems or the microscopic inner workings of CPU registers, this exact same logical structure applies across the board. You start simple, you add the technical vocabulary, and you shape the response into the exam style. You identify, you explain with context, and you run that final self-check. This step-by-step methodology transforms textbook knowledge, which, let's face it, is static and easily forgotten, into a dynamic, full-mark solution path that you can deploy no matter what specific scenario the exam throws your way. So, to wrap this all up, memorization is a trap. Logical reasoning and contextual application are your true keys to full marks. If this explainer made these concepts click for you, make sure to keep following along so you can absolutely excel in your Cambridge examinations. Keep practicing that 4-step check, but I want you to ask yourself right now, honestly, are you going to keep blindly memorizing textbook definitions, or are you finally ready to explain the mechanism and totally dominate the mark scheme?